I hope my screen's visible.
Yes, sir.
Okay. Welcome everyone to today's session on passwordless authentication. This session is a little unplanned. We actually had planned for a very elaborate session, but most of the team is sick, so we had to make some last minute changes. So apologies for that. Now we'll get on with the session. So in this session, we are going to discuss the various authentication models available, and then some basic concepts of asymmetric cryptography. It's mentioned as RSA. RSA is an algorithm that is used in asymmetric cryptography, but we'll be discussing broadly about asymmetric cryptography. And then we will be looking briefly at trusted computing and one of the authentication mechanisms that rely on trusted computing, which is FIDO2. So if you look at authentication in general, when I say the word authentication, the most popular thing that will occur to you is password-based authentication. When you want to log into a website, it will usually ask you for a password, right? And there are some drawbacks to this password-based authentication. It's the oldest form of authentication, but it's not good enough. So what are those drawbacks? It's vulnerable to brute force attacks, meaning you can try various combinations of letters and then you can, get around the authentication mechanism, which isn't good. In fact, the time taken between a 7-character password, the time taken to break a 7-character password and the time taken to break an 8-character password is just massive. 7 characters, you can, if you get your computer running for a full 4-month period, you will be able to break 7-character alphanumeric password. But if the same thing were an 8-character password, then you're looking at over 4 years of heavy computation. But because of weak password usage and password reuse, we can cut short this time exponentially. So there are popular password lists. You can simply Google for password lists and it will give you a bunch of things with 10,000 or even 10 million popular passwords from popular database leaks. And what you can do is that you can write a script to read every single entry in the password list, and then you can try different combinations from the entries to get into the application. And this is because people reuse passwords all the time. In fact, a survey from Splash Data states that the most used password between 2011 and 2018 were password and 123456. So if you're using this kind of password, the hacker will require barely like 30 seconds of computation to break into your account, and that is not good. Sure, you can say that the fault isn't in the mechanism, but it's in the user. But a secure mechanism will not give the user a lot of room to commit mistakes. And when we're talking security and authentication, then we have to keep this thing in mind. It's the most important thing in any security mechanism for authentication. So how are authentication mechanisms designed? The first thing is something that the user knows. This will be something like PIN, password, or your mother's maiden name, such kind of questions. The idea here is that if a user can reproduce the information, then they are who they claim to be. And so the user is authenticated. And the second one is something that the user has, meaning nobody else will have it. There has to be that uniqueness attribute to that item. So this could be anything like ATM cards, phones, security keys, and etc. And the third one is something the user is. And this could be something like fingerprints, iris scanner, if we have that sort of thing around, voice recognition, things like that. And then the fourth one is something that the user produced. This could be speech recognition and signature, the one that we sign on paper. There's a different kind of signature we'll be getting to at a later point in the presentation. This one's, however, the one that we sign in paper. Actually, this could be the other thing also. Yeah, this could be the cryptographic signature also. So when you talk about single factor authentication, it usually relies on one of these methods, just one of these methods. But when we're talking about multi-factor authentication mechanisms, it will rely on at least two of these things. The idea here is that if one of these things is compromised, let's say you are using a service and that service has suffered from a database leak, your password will be available to the hackers or anyone on the internet really. If you give it enough time, it will be available to anyone on the internet. So if that service that you're trying to log into uses only the first mechanism, that is something that the user knows, then your security is compromised, right? But let's say there is an additional mechanism. Let's say they're using something that the user has. This could be like an OTP also, OTP from an application like Google Authenticator, which uses a mechanism called TOTP. So when there is an additional authentication mechanism, the hacker cannot do anything with just the password. They will have to attack the other mechanism also, and then they will have to compromise it. This may sound simple, but it increases your security exponentially. So good authentication mechanism must rely on at least two of these things. It cannot rely on just one thing. Now, like I said in the previous slide, passwords have the disadvantage of being lost and being, anyone can provide it. Likewise, there are disadvantages to every single model also. And we'll look at some of those now. The first one's password. Like I said, it can be extracted by anyone. And one of the mechanisms that can be used is social engineering. I mean, phishing, which is a social engineering mechanism. A phishing attack is essentially one where an identical website is produced, but it's not the authentic one. Meaning, let's say you're trying to log into Gmail. A similar website that looks exactly the same, down to the last tiling element. But it will not be the one that is run by Google. It will be run by the malicious actor who will try to convince you that this is the real thing. And if you don't verify the website properly, you could be entering your credentials into the wrong malicious website. So using that mechanism, you can easily grab your victim's passwords. So that's phishing. And then something that the user has. This can also be compromised using phishing. Let's say that the form where you have to enter the OTP is compromised. It's from it's run by a malicious actor. What the malicious actor will do is that they will collect the OTP from that form, and then they will replay the same OTP to the original service. All of this will be automated and will happen within a matter of seconds. That way, like, you won't even be able to stop the attack in progress. So that's OTP phishing. And the other thing is ATM cards can be skimmed. Now, this is no longer the case because these days ATM cards come with chips, right? Before that, RFID used to be the main thing. So when that was the case, you could get card skimmers which look exactly like the point of sale machine that you see in departmental stores, except it will be able to read every single identifier in the ATM card. So once you have the identifier, you can burn the identifier into a different mag stripe card. You can get these things for like 30 pieces, like 10,000 rupees or something. It's really cheap, mag stripe cards. You can get those cards and burn this identifier on those cards. And then if you go and insert it into an ATM, it will work just like the real one. So that's how you get ATM cards skimmed. And then the third one is biometrics. Now, despite the prevalent opinion that biometrics are secure, it can be cloned. Fingerprints can be cloned, iris can be cloned. So relying entirely on biometrics is not a good idea. And then the third one is something that the user produces. Like I said, OTP with that man-in-the-middle replay attack, It can be captured, and if there are not proper replay mechanisms, it can be replay protection mechanisms. The same stuff can be used again to get through the authentication mechanism. Now moving on, passwordless authentication. Like I said, passwordless authentication is based on something the user is, right? I mean, something the user has, and that is not secure. There are a few instances where the service provider will send you a link to either through a side channel, using a side channel like email, or sometimes even messaging platforms. Like for instance, if you're trying to log into Telegram, the Telegram website will send you a login link or a code through the mobile application. So that type of authentication is called magic link, which also fall into the passwordless authentication mechanism. In both of these things, your security is dependent on your ability to safely retain the secrecy of your password, or in Telegram's case, your Telegram application. So if you lose your device, the malicious actor will be able to log in pretending to be you, and that is not good. Now, because passwordless authentication is insecure due to all the reasons that we have discussed so far, we will be discussing some of the other mechanisms that can be deployed to enhance the user's security. And one of those mechanisms rely on asymmetric cryptography. When we generally talk about encryption, we usually think, there is a password, you enter the password to encrypt something, and then if you share the password with someone else, they will be able to decrypt the password on their end, right? That type of encryption is called symmetric encryption, because both parties, the encrypting party and the decrypting party, is aware of the secret, which will be a private key. But in asymmetric encryption, the password will be known only to one person. This also ensures that if the data is encrypted, then it can only be decrypted by the other party. Even the person that originally encrypted it, right? They won't be able to decrypt it if they lose the underlying data. And we'll see how it works. In asymmetric cryptography, there are two keys. You can think of them as two passwords. One is called the private key, and the other one is called the public key. So let's say you want to take part in a system that uses asymmetric cryptography. What you'll do is you'll firstly generate a key pair, which will be your private and public keys. You will retain your private key, and then you will keep it secret. You won't share it with anyone. You will, if you're really serious about your security, you'll take a printout and store it in your bank locker, like I do. But the public key can be shared with everyone, and you can use it to, you can attach your public key to emails. You can attach it to your website. There are even dedicated key servers to which you can, send your public key and tell them to store it on behalf of you, so that if someone wants to send you a message, they can simply search in that key server and get your public key. And the way this thing works is that the stuff that you encrypt with your public key can only be decrypted with your private key, and the stuff that you can encrypt with your private key can only be decrypted by your public key. We use this method in authentication using a procedure called cryptographic signing. And this is basically you encrypting some data using your private key. Like I said, if you encrypt something with your private key, only the person, you can only decrypt it with the public key, right? So, and since you're the only person with access to your private key, you can use it as a mechanism to say that, since I'm the only person that has access to the private key, if you see my signature, or if you see some data that can only be decrypted with my public key, then you can assume that it was signed by me and me alone. So that's a way of authentication. And to do this whole process, we use something called trusted computing. This is a hardware module that is found in modern CPUs with the latest Windows 11 update. everyone seems to be aware of this thing. And the way this works is that it will retain your private key in the hardware itself, so that it is not leaked to other processes. So in operating systems, there are multiple security pitfalls. If you look at the oldest forms of operating systems when they were first launched, I'm talking about 80s, the security mechanisms were practically non-existent. Any process can read from any other process memory. So let's say you're operating on a compromised machine, meaning it has a virus installed on it, and you're trying to encrypt some message. To encrypt the message, you will provide your private key, right? And this private key will be stored in the processor's memory. In those days, any process can read memory without any restrictions, and they will be, if a malicious program is running, it will be able to grab your private key. And even with advanced memory protection mechanisms, this has still been a problem. So what people did was that they created this trusted computing platform, and then it is designed in a way that only one process can access it at a time, and whatever goes in there cannot be read again. It retains the private key. Some of the programs that use private key are Samsung Knox and Google Titan, Windows Hello. I don't know how Windows Hello works, and then Apple's Secure Enclave. So that's about private key authentication. But the most popular way to use private keys, use asymmetric cryptography authentication is using physical keys. You might have heard about these things if you're interested in cryptocurrencies. There are things known as hardware wallets, which are basically the same thing. What they do is that they will save your private key onto the hardware itself. And then, like I said, for the authentication mechanism, you have to sign the data using a private key, right? So this hardware will be capable of receiving messages, and it will also be capable of signing it for you. And after signing, it will send it back to you. So the whole private key thing is contained in the hardware itself. The only thing that is going back and forth is the data and the signed message. And these hardware keys have various interfaces. You can use it using USB. This particular image is called a YubiKey hardware key, and that works through USB. They can also be used via BLE or NFC. Now, Aditya Mitra will carry on about FIDO and how FIDO works. Aditya, are you available?
Yeah, thank you. Is my screen fine? Hello?
Yeah, your screen is visible and you're audible. Please go ahead.
Okay, thanks. History of FIDO. 2012 to 2013, FIDO Alliance was founded and launched publicly. February 2014, PayPal and Samsung collaborated for the first FIDO authentication that enabled the Galaxy S5 user to pay in a passwordless mode via PayPal. December 2014, FIDO UAF and U2F protocols were published. December 2018, FIDO UAF 1.1 and VIT-AP were recognized as international standards by ITUT. In March 2019, WebAuthn became an official standard, giving rise to FIDO2. So let's authentication demo with FIDO2 on Microsoft. Please watch the demo. Here we ask for the security key and we are logged in. Simple. FIDO for multi-factor. So for the username and the password, and then it asks for the FIDO key. Components of FIDO2. These are client browser. This is the web browser we're using. The authenticator attachment is the physical security key or internal trusted computing module. It serves two types. Platform is the internal authenticator and cross-platform is the external security key. RP server is the website we are logging into. RP ID is the URL of the RP server. Challenge is a small text which can be encrypted and decrypted to check whether the key pair used is valid. Specs in FIDO2. W3C WebAuthn is the set of protocols that defines how the RP server interacts with the web browser. Client to authenticator protocol VIT-AP is the set of protocols that define how the web browser interacts with the authenticator attachment. Here is an animation which shows how the key is registered. Let's see. Registration request is sent from browser to RP server, and the RP server replies with a challenge, which is forwarded to a security key. The security key generates the key pair and signs it. The public key and the signed challenge is sent back to RP server, which is then checked. Animation for the authentication process. Login request is sent to the RP server, and RP server replies with a challenge and RP ID, which is forwarded to the key. The key signs the challenge with the saved private key, which is forwarded back to the RP server, and which is then verified, and the user is given access. What makes FIDO2 strong? It's the use of PKC, use of trusted computing, where the private keys never leave the hardware. RPID is verified at every step to stop man-in-the-middle attacks. This cannot be phished, as the client is verified by RP. User does not have to know any information to be able to log in. This follows the zero trust model. These are some resources you can use. Thank you.